Oh hi! Welcome to this video on thermodynamics. In this video we're going to talk about the Zeroth Law of thermodynamics, which, as I said in the introductory video, is the law that defines what is meant by the word temperature. As I said in the introductory video, each of these laws actually defines one of these words in thermodynamics. For instance, the first law will define what is energy and what is work. The second law will define the entropy. And of all these words that I just mentioned, temperature sounds like the one that should be easiest to define. Because after all, temperature is something that all of us are used to from the moment that we are born to the present day. Namely, temperature is something that we can measure, register with our bodies. It's a bodily sensation. So it sounds a little bit strange that of all these abstract concepts like entropy and energy, temperature is the one that needs defining. But it does. Because temperature really is not a very easy concept. In fact, if you were to ask somebody, please define what is meant by temperature, and please don't do it just by saying, well, it's what I feel with my body, we need a more rigorous definition, then a lot of people will probably say something along the lines of, well, temperature is how hot an object is. Okay, what do you mean by hot? And then they might say, well, hot is that it has a high temperature. But then you have circular reasoning, yes? I mean, you're saying that temperature is defined by hotness, but hotness is defined by temperature. That's circular reasoning. And we're really just kicking the ball around here a little bit because we just replaced the word that we didn't know, temperature, by another word that we also don't quite know how to define, namely hotness. So that way of looking at it really doesn't work very well. Now, people who have already started some of the natural sciences might say, aha, but I know the temperature is related to this other concept called the energy. So a hot cup of tea might have something to do with the fact that there is more energy in that cup of tea than in a cold cup of tea. Now, that is sort of true. There's many nuances there, but it's not completely true either. First of all, in order to define then temperature by means of its energy, you also have to define what is meant by energy, and we haven't defined it yet because that's what we only will define at the moment we're going to introduce the first law of thermodynamics. But most importantly though, in substance like tea or a cat or a banana or the whole universe that has a high temperature is not necessarily a substance that has a high energy. In fact, I can take a substance, I can squeeze a lot of energy in, yet the temperature will stay the same. That's completely something you can do in the laboratory. So the idea that temperature and the amount of energy that is in a system are related directly to each other is simply not true. It's measurably untrue. So yes, they are related, but not in this very simple way. So we cannot define temperature just by means of talking about the internal energy of a system. So we really have to do a little bit better. Now, some final thing that people might say when you ask them what is temperature is that they say, well, it's the amount of bounciness of the particles that is in that substance. That is in some cases indeed true. If you take a cup of tea, for instance, yes, and it is very hot, then on a microscopic level, the particles are bouncing a lot against each other. And that is what our body feels. It feels the bouncing, well, not individually, but the net effect of the bouncing is indeed exactly what our body feels as a temperature. So there is some truth in that definition, temperature as the measure of bounciness of particles. But there's problems there too, unfortunately, because first of all, thermodynamics is a study of macroscopic systems. So if we're going to tie our definition of temperature to the microscopics, what happens on a very small scale, then all of a sudden our definition of temperature is going to depend on, well, the microscopic details of a substance, and we are looking in thermodynamics for a theory that explains everything. So it should not depend on the small thinginess of this substance versus that substance, otherwise you will get a different definition for temperature depending on what substance you happen to be looking at. But there's another reason why we should not tie the word temperature to bounciness of particles. And that is that in physics there's a lot of systems that don't consist of bouncing particles. Light, for instance, right? If I have a bath of light, light comes with a temperature. You can feel the temperature of light, yet there's no bouncing particles there. Let's take an example. After the Big Bang, about 400,000 years after the Big Bang, light started to shine in the universe. This cosmic microwave background has a temperature that one can measure. It's well measured. It's about 2.73 Kelvin, so 2.7 degrees above absolute zero. But there's no bouncing particles in light. So the definition of temperature in terms of bouncing particles, well, that works at the moment that things are actually made of bouncing particles. If it's not, then you can't define temperature in that way. And we are looking again for something, a definition that holds for all systems, whether they're made of bouncing particles or not. So I hope I've conveyed to you now that temperature is really a difficult concept to define, even though it's the one that we might be bodily used to the most out of all these other sensations that we have here. So let's define temperature. The Zeroth Law is the one that does it for us. In fact, people realize that the definition of temperature is actually more important than the definition of energy, and it's more important than the definition of entropy. When I say more important, what I mean is that if you start with the definition of temperature, then the other definitions can follow from that one. It's the foundation of the other definitions is in part based on the definition of temperature. And when people realize that, they had to, well, put that into law. But unfortunately, there was already a law that's called the first law, so this somewhat more important law had to go in front, and therefore it's now called the Zeroth Law. That's no joke, it's literally called the Zeroth Law of thermodynamics. Now, what is this law? The law is actually an experimental observation. And the experimental observation is so obvious that you might actually overlook it. It's an observation that everybody is used to, but you are easy to overlook it, to see that there's something special going on, and that it leads us to the definition of temperature. What is this observation? The observation, verbally put, is simply this. If you have a piece of nature, doesn't matter what it is, could be banana, could be a cat, could be the universe, could be a cup of tea, and you put it next to another piece of nature, could again be anything, you put them together, then both of these pieces of nature, both of these systems will change their internal numbers. Things will not stay the same, they will start changing. And at some point they will stop changing, and then, well, they're both in a new situation, a new state is what we call it. And then they stay there unless you start putting another piece of nature next to it or start touching the thing. So the observation is simply this. Piece of nature, another piece of nature, put them together, and the numbers will change, and at some point they will get to a new equilibrium and they will stop changing. Completely obvious. If I take my cup of tea again, I put it in my hand, I can feel that my hand is not going to be the same before I touch the tea, and the tea will also feel that it will become slightly different. My hand, for instance, will, if you measure very close, it will expand by a small amount. Tea, if you just leave it over there here in the room, that means you also put it in contact with another piece of nature, namely the room, at some point will also change its situation, its state. If you wait very long, for instance, the volume will go down, 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 because the tea will evaporate into the air. So numbers will change at the moment that you put two pieces of nature together. I'm going to draw that here, and as always, I need something to point at, and historically in thermodynamics we take gases to point at. But I want to stress, and I keep on doing this in all these videos, my examples, what comes out of this is not going to be contingent on the examples themselves. You could replace my gas with something else and you would get to the same conclusion. But I'm going to take a gas because it's easy to point at. Okay, here's a barrel of gas. And it has a piston, right, a lid that can slide up and down. And in here is where the gas lives, and it's a completely sealed container, so the gas cannot come out. At this point, we can say that the gas is completely isolated. Now, a gas comes with a number of numbers that describe its state. For a gas, that could typically be the volume. The gas takes up a certain amount of cubic meters that we call the volume V. Gases also typically come with pressure. How much is the gas trying to push against the walls of the container and to the piston? That we call P. And depending on how difficult you want to make your example, there's many more numbers that you can assign to the gas. For instance, if the gas happens to be electrically charged, you have to put the electric charge in there. And maybe there's more than one type of atom in there, then you have to put in there something that's called the chemical potential and all these difficult words. So you can make this list of numbers as long as you want, depending on your situation. Same with bananas, by the way. Bananas also have a volume and they have a certain amount of pressure. So what I'm saying here holds for all systems that I care to look at. Now, for simplicity, I'm just going to look at a gas that only contains a volume and a pressure, just to make my example a little simple. Okay, here's an isolated piece of nature, and I'm going to put another piece of nature next to it. This again could be my hand when I hold the container in my hand, like I do with a cup of tea. Now, this other piece of nature, again, could be anything, could be my hand, could also put a cat or a banana against this gas, but again, I need something to point at, so I'm just going to take a simple example, another gas. So here's another barrel of gas, which has also a lid. So this other gas lives over here, and the two containers are separated from each other. The gases cannot mix. There's no leaking between the two containers. Now this other gas also comes with numbers that describe its state. It could also come with a volume and a pressure and all these other numbers, in case you want to make the example more sophisticated. I'm going to put a little prime on top of this V, just to indicate that it's not the same as this volume, and a little prime on top of the pressure to indicate that it's not the same as this pressure. It's different numbers. In fact, you can see this in my picture. This volume is a smaller number than this volume, and the pressure is probably something else too. This I'm going to call situation number 1. Okay, two gases put together. The zeroth law is just the observation that if you put two pieces of nature together, then these numbers are going to change. So if I wait for a bit, this arrow just means I'm going to wait. This number V is going to become different. The gas is going to expand or become smaller. The pressure is also probably going to change. The same with these two volumes and pressures. And at some point they will stop changing. So here's the same situation, but now a certain amount of time later. And well, it depends on the circumstances, whether it was a cat or a banana or what type of gas it is, how exactly they have changed. It doesn't matter for my conclusion. So I'm just going to make up a situation. Let's say that this gas has moved up. Yes, it has expanded. So the lid is not here anymore. It's now all the way up there. So it will be here-ish. There you go. So the gas is in a much bigger volume now. And suppose that the volume of this one, you know what, has also risen by a small amount. So it was halfway, it's a little bit above halfway now. There you go. Then the other gas is also in a different state. Let's assign some new numbers to it. This was called V before. Let's put a 1. This was the volume at moment number 1 and the pressure at moment number 1. The same here at moment 1. In the new situation, the volume and the pressure will be different numbers. Volume 2 and pressure number 2. The same with this. It will be a different volume, volume prime 2 and pressure prime 2. Possibly the volume and the pressure are related to each other, but that depends on the type of gas. Okay, that's not the point here how V and P are related. It's called the equation of state, how the numbers in the system are related to each other. That's not the point here. The only point is that the numbers are not the same anymore, and how they have changed, that's not the content of the zeroth law, just the fact that they have changed. So the situation has now changed. Again, no mystery is going on here. This is just what you know from everyday experience. When things start touching each other, they will change their properties. That's what happens here. This is simply the observation, and it's so obvious that nobody even cared to call that a law. But then people realize there's a question here, and that question will lead to the definition of temperature. Here's the question. Okay, the numbers changed, went to these two numbers. How did nature know when to stop? You put things together, the numbers will change, and at some point they stopped changing, right? It became a new stationary position, we call this equilibrium. How did nature know when equilibrium was reached? By what criteria did nature decide that it should stop the changing of these numbers? That's a very difficult question. How did nature know? Now let's take some naive guesses. One guess could be, you know what, maybe nature as a criterion is using that it should stop at the moment that the volumes have become the same. So nature, if you put these two together, will try to make the volumes even each other out exactly, so that the amount of cubic meters here is exactly the same as there. Now it only takes a couple of experiments to find out that that is not the case. Yes, you could already see this in my drawing because the volumes are not the same, and this is something you can simply measure in the laboratory. You put two pieces of nature together, it will not stop just because the volumes are the same. In fact, usually they're not. Same thing with the pressures. Maybe the pressures have become the same. And it turns out, in its generality, this is also not the criterion that is used. So nature is not looking at the volume or the pressure a piece to make things the same. So that's not the criterion here. Now you can go through the whole list because hypothetically you can put as many other parameters in there as well, like the electric charge or the types of gases in there. And you can go through the whole list of these two and to compare the numbers to each other to see if there's any matching number at the moment that they stop changing. And the answer is always no. There might be some cases where some numbers happen to be the same, but generally speaking, the whole list of numbers that make up the state of the system will not change so that some of these numbers have become the same. So that really exhausts our possibilities. I mean, how many more things do we have? We only had these numbers and those are not going to be the same. So apparently nature is choosing some other criterion to determine whether it should have stopped changing. And then people decided, you know what? That is by definition then the temperature. We can define temperature as some number, apparently it's not these numbers, but it's some number that tells nature that it should stop changing the numbers, the other numbers, the V's and the P's. So there is some number that you can construct out of these. So each a piece doesn't work, but there's some new number you can construct out of the existing numbers. And it's that number that is going to be the same, and that tells nature when the changing should stop. So that is by definition what is called the temperature. The temperature is the hypothetical number, some function of the other macroscopic parameters, such that if that number is the same between the two systems, this is when nature will stop changing. So that defines what is meant by the temperature. Now note that one can only make this definition at the moment that the Zeroth Law holds. Because suppose that the Zeroth Law would not be true, that if you put two pieces of nature together and they would not start changing, or they change but they never stop changing, then there is going to be no fixed number with which you can determine that the two systems are the same. In fact, let's reiterate that point by taking a cup of tea. There you go. And suppose that I would like to know what its temperature is. Now, by definition, the temperature is the number that should stop changing at the moment that I bring it in contact with another piece of nature. This other piece of nature is what we call a thermometer. A thermometer, in the old days, for instance, was a tube that was filled with a liquid. Here's a tube with a liquid. This was before we had electronic thermometers. Before, what people did was they just took a tube and they put some liquid in there. That was typically liquid mercury. And at the moment that you stick the thermometer into your cup of tea, the liquid will expand, the volume will become bigger. This, by the way, is exactly this situation. Yes, this is your cup of tea. You bring it in contact with some other piece of physics, in this case a thermometer or a tube of liquid, and then the numbers will change. The volume of my tube of mercury will increase, and then you see the mercury rise. So it used to be here, but then it goes all the way here, then it goes all the way there, then it goes all the way there, then it goes all the way there. And at some point it will stop. And then people who make thermometers just put a scale on there that you said, well, we're going to take the expansion of the volume as our measure of temperature. And then they say, well, if it stops over here, we call it 70 degrees, this is 60 degrees, etc. So it's by the Zeroth Law that one can define a temperature. If, again, the Zeroth Law had not been true, that sticking the thermometer in would not have changed the state of the volume of the thermometer, of the liquid mercury, then you could not use it to measure anything because it would just stay the same. And also, if it never stopped changing, it would move on indefinitely, and you could also not assign numbers to it. So, Zeroth Law simply means one can define a thermometer. Now, that's all quite obvious, but here you can see that I've not quite really defined yet what is temperature. In my example with this old thermometer, I really just replaced the volume, this volume that will be the volume of my liquid mercury, and I just called it the temperature. Yes. Why didn't I take the pressure? I'm going to measure the pressure of the mercury and take that then as a measure of temperature. Well, that's up to us to decide. We only need to have that there must be some number that for which you can read that the system is not changing anymore when brought into contact. Which of the existing parameters you take as the temperature is up to us to decide. In this very simple example, I simply took the volume of my thermometer or my liquid mercury, but I could have taken the pressure, that's fine too. In fact, what I could have also done is take the volume and the pressure and make some mathematical formula out of that and define that as the temperature. That's completely up to us to decide. Which choice we make is just a matter of practicality. We just have to decide. So originally people took these because mercury in a liquid in a tube is very easy to measure, and pressure is a little bit more difficult to measure, so it's an obvious choice to make. But it is free for us to decide. Now, if you stick your thermometer in, it's not just the volume of the liquid that's going to expand, right? There will be this volume that's going to change, but my cup of tea will also change its parameters. So one can then ask, okay, but why did you take your thermometer, your liquid here as the thermometer? Why did you take that one as a measure for temperature and not a cup of tea? Again, that is up to us to decide. We just need one of these systems and then some user-chosen combination of their parameters that we're going to take as the temperature. Doesn't matter which one you use. Now, it's more handy to use the tube of mercury as the measure for temperature and not the cup of tea, because that means if you want to compare your temperature by somebody else in a different laboratory with their temperature, they need to have the exact same cup of tea as yours, which is not a very practical measure, not a very practical thermometer. If you're going to define a thermometer as some system that everybody can use, and in this case just measure the radius of the volume, well, then you need that system to be freely available to everybody and not dependent on how much sugar that person put in their tea as opposed to the other person who put that into their tea. Tea is not a good measure for thermometers. But liquid mercury is, well, it's available, right? It's the same everywhere. So this is why people originally took this. Now, then you can ask, okay, but how then do you know that everybody will measure the same temperature? Well, liquid mercury is the same everywhere. So as long as people, all of them, use liquid mercury, it should be all the same, yes? That's easy enough. So we just need some of all the things that you can put together which will change the numbers. We just have to choose some particular piece of nature to use as the thermometer, and then one of those parameters within that piece of nature as the temperature. Now, I've been harping a little bit on this particular example of the liquid mercury as the thermometer and the volume of the liquid mercury as the temperature. But again, this is user defined, and people later found that there are other measures that are slightly better or slightly more practical. So this one is not in use anymore, but it was the easiest to explain here and now. So that really sums up the Zeroth Law of thermodynamics. It allows you to define temperatures. There's a related concept that is called heat. I already mentioned this before. What do we mean by heat? Well, heat is a form of energy, as we will see in the next video, but let's not go there at this point yet. Heat is some hypothetical substance that is transferred in between the two systems that makes the systems change, right? If the systems change, as the Zeroth Law tells you that they do, there has to be something transferred from one of the systems to the other. Let's say that the transferring went in this direction. That transferred stuff, whatever it is what we call by definition heat. So heat is written by the capital letter Q for some reason. Heat is simply defined as the stuff that apparently is transferred from one system to another at the moment that the Zeroth law is doing its thing. We haven't defined yet that heat is therefore a part of energy. We will see that in the next law. We just have defined that something was transferred from one system to the other, and that something is what we call heat. And here you can clearly see that heat and temperature are not the same thing. Heat is defined as the stuff that's being transferred as the Zeroth law is doing its thing. Temperature is defined as the number that becomes the same between the two systems when the heat is done transferring. So you can clearly see heat and temperature are not the same thing. So one more time, heat is the stuff that's being transferred due to the Zeroth law. Temperature is the number that becomes the same at the moment that the heat is done transferring. At the moment that the Zeroth law is done doing its thing, the system has gone to a new equilibrium, then the number that says that it's done with transferring heat, that number is called the temperature. Completely different things. So it is somewhat confusing, therefore, that some systems actually do have a relationship between temperature and heat. So I'm just going to write this down for completeness, but don't memorize this as being true in all systems. In some systems, it turns out that dQ, Q by the way is the heat, but in dQ is a small amount of it, a small amount of heat, that dQ is actually linearly related to the rise in temperature. That every time that you increase the heat twice, the temperature will increase twice. Now it does depend on the substance, so there's a number in between the rise of the heat and the rise of the temperature, and that number is substance dependent. It's different for different gases and different materials, and it's called the heat capacity or the specific heat. And I put a little V in here because it depends on what the rest of the system is doing. If heat is transferred, but you keep the volume of the system the same, so in my example it will be that I make sure that the lids cannot move up and down, then this is the heat capacity, some number at the moment that the volume is kept constant. You can simply measure it. If you measure the heat and you measure the rise in temperature using, for instance, a mercury thermometer, you can measure what this number is and you'll find a different number for different substances. Now you can also transfer heat from one system to the other and see the temperature rise, but this time you do allow the volumes to become bigger or to become smaller, so you don't keep the volume constant but you keep the pressure constant. Then you will find that in some substances the rise in heat and the rise in temperature are also linearly related, but now with a slightly different number in between. It's not CV, the heat capacity at constant volume. There's another number, the heat capacity at constant pressure. So you have to be a little bit careful when you talk about heat capacity, which of the two you mean. There is some relationship between the two, but that's something for the proper full course in thermodynamics. I want to stress here that these two relationships hold for some cases. It's certainly not always the case that heat, so adding heat to a system, will result in a rise of temperature. You can have systems where you put heat in there, but the temperature stays the same. So you have systems where dQ is non-zero and dt is zero, and then this relationship doesn't hold anymore. But there are substances where this formula holds by good approximation, so therefore it was worthwhile to mention this. So please don't memorize this as saying, oh look, so that means heat and temperature really are directly related to each other. It's only in some cases. That brings us to the end of this video. So what we have seen now is the Zeroth law. Just to reiterate, the Zeroth law says put two pieces of nature together. They will start changing their numbers. We say in practice heat is being transferred from one system to the other. When does nature know when to stop? Well, at some point it stops, and that stopping moment we define as saying that the two systems therefore have the same temperature. That doesn't define the numbers that you assign to temperature. That's up to us to decide. We have to decide which of these systems we take as the thermometer, and within that thermometer which of those numbers, V and P or any of the other ones, we take as the temperature, or maybe even some combination of these things. But once we have that, we have a definition for thermometer, we have a definition for heat, we have a definition for temperature, and we're all good to go. In the next video, I will show that this heat is actually related to energy. In fact, heat is a form of energy. And we're going to see that this is not the only way that you can make systems change. You can make the numbers of a system change by, again, letting the Zeroth Law do its work, combine it with some other system and let heat transfer. But there's another way of doing it. If I don't connect it to some other piece of nature, like this, so I have an isolated system now, I can also change these numbers by doing manual work. I could, for instance, if I want to change the volume, just press down on the lid and then the volume will change because I do something to it. Now that you might know from your mechanics courses, Newton's laws is a form of work. That's what we call work. If you press on something, you perform a force on something. We say that you are performing work on the system. In the next video, we'll see that this work, this W, that you can use to change a system is actually of the same type of stuff as this heat thingy that was transferred when you let the Zeroth Law do its thing. And so we will see that heat and work are actually the same sort of stuff, and that sort of stuff in its totality, that is what we're going to call the energy. So here you see we really needed the Zeroth Law defined first before we could move on to the definition of energy. But for that I invite you to go to the next video.